Hello and welcome back. In the last two videos, we were discussing communications and communication protocols. We ended with discussing the 8251. In this video, I'm going to be talking about a completely different device that one can interface to the 8086, actually the 8086 series of processors. It's called the arithmetic coprocessor. The challenge of using a general purpose CPU like the 8086 for complex arithmetic functions is two. One is that it consumes enormous programming bandwidth. You really need to spend a lot of time programming the algorithms that you want. If you wanted to do floating point arithmetic, exponential arithmetic, etc., you need to write programs that are fairly complex. And the second one is it slows down the processor tremendously, slowing down the complete system. And that's why Intel came up with this concept of an arithmetic coprocessor. And for every version of the general purpose CPU, so 8086, 80186, 80286, 80386, and so on, there is an equivalent arithmetic coprocessor. In the case of the 8086, it's the 8087. So let's look very briefly at what the 8087 is. As I said, it's an arithmetic coprocessor. It is designed to work with the 8086, right? And it performs only floating point instructions. So it obviously saves time and programming effort for the 8086. It also provides an additional 68 new floating point instructions. So if you remember the instruction set of the 8086, you have the basic add, subtract, multiply, etc. This one gives you 68 instructions dedicated to floating point arithmetic. And on top of that, the 8087 operates in a slave mode with the CPU. So the CPU continues to be the master, of course, but the 8087 works as a slave to this device. And as far as the CPU is concerned, it is happily ignorant of the existence of an 8087. It's just transparent to it. And I'll tell you how this works. So how does the 8087 interface with the CPU? Right? So what really happens is, as I said, this is a master-slave configuration. The CPU, the 8086, fetches instructions from the program memory, and as a programmer, you just assume that the 68 additional instructions are part of the 8086. So you can write a program that interleaves 8086 instructions along with the 8087 instructions. It just flows like a normal program. And the moment an 8087 instruction is recognized, so all 8087 instructions start with an escape code, ESC, the escape code. So the moment an 8087 instruction is recognized, it is automatically handled by the 8087. The 8086 completely ignores it. Not completely, it ignores the instructions, but helps the 8087 execute this. And we'll tell you how that does this. So 8087 executes the instructions, and the results may be reflected back to the CPU at the appropriate time. Let's see how this works, right? So first of all, the 8086 is connected to the 80, so there is obviously the hardware interfacing, which is really the data and address lines. There is something called the request and grant signal, RQ1, RQ0, which is used as interface between the 8086 and the 8087. And it is used to inform the CPU to hand over control to the 8087 at an appropriate point in time, typically at the end of the current bus cycle. The QS0 and QS1 informs the 8087 on the status of the code prefetch by the processor. And both the processor and the 8087 must look at every instruction and decide to which part of the system it belongs to, whether it belongs to the general purpose CPU or the floating point CPU. And the 8087 will interrupt the CPU through the 8259. You remember our 8259 discussions? So the 8087 will interrupt the CPU through the 8259, and you as a programmer must decide what to do with that interrupt. So you could choose, as soon as the interrupt occurs, to collect the data, to collect the results of the floating point operations. How does this really work? How are they so intimately connected to each other? So what really happens is the CPU and the 8087 both look at every instruction. Remember, they are both connected to the same address and data bus, and the memory sits on the same address and data bus. And the CPU and 8087 both determine if a specific instruction is meant for the 8087. If it is, then the CPU fetches the first word of data that the 8087 will need. So both of them have recognized that this is an instruction for the 8087. The 8086 then fetches the first byte of the operand. So floating point instruction, remember, can contain up to 10 operands, so 10 bytes of information. So after sending this word to the 8087, the 8087 will then use this data and acquire any additional pieces of information it requires directly from the memory. So the 8086 is no longer part of this data fetching. Only the first byte is fetched by the 8086. Subsequently, all other bytes that the 8087 needs is automatically fetched by the 8087 on its own. It takes control of the data and address bus. And if at the end of this, hopefully the 8087 has enough data, all the needed data to execute the instruction. The instruction is executed and control is handed back to the CPU. The CPU continues with the program flows. Just both of them again start looking at all the instructions. This is how the two really interleave and work with each other. They cooperate with each other in this manner. The 8087 can generate a bunch of exceptions, right? I mean, it is a processor on its own, and there is a possibility that multiple errors can occur. So what are the kinds of exceptions that an 8087 can, so the exception is really the errors. One is that it is an invalid operation. So for example, you cannot, the 8087 will not be able to deliver the square root of a negative number. It just doesn't exist. It could be an overflow, and that's an exception. So the destination format, for example, it's a word, is not large enough to store the result of an operation, which may require a double word. Right? So it says there is an overflow error. It could be a zero divisor. So that means you're really dividing something by zero. Again, an undefined operation. It could be what's called a denormalized operand. And a denormalized operand is a special case of an underflow. So what's an underflow? An underflow is when the result is extremely small and cannot be represented in the typical floating point arithmetic. The denormalized operand is a result that is so small and so close to zero. And you have, as a programmer, to decide within the 8086 what to do with these kinds of exceptions. The last kind of exception that the 8087 can deliver is something called an inexact result. And this is because during the operation, so during the execution of the floating point arithmetic, the 8087 has decided that there is a potential for inaccuracy. Typically, this inaccuracy is very small, but again, it leaves the options up to you as a programmer to decide what to do with this inaccuracy. All these exceptions can cause an interrupt of the processor, and if the processor is interrupted, the processor can poll the 8087 to determine the exact kind of interrupt. The last piece that I would like to discuss is really about the 8087 stack. It is unique. Now remember, the 8087 is a processor. It needs an accumulator. And the way that this has been managed is by assuming that the top of stack, called ST0, is the accumulator. And there are really 8 stack locations identified for use, and this is a rotating stack. And what you will see in this diagram is explaining how this rotation occurs. So the top of stack moves, so the stack pointer really moves to the next location of the stack, and everything rotates after that. And it is your responsibility as a programmer to maintain the integrity of this stack. You cannot obviously use more than 8 bytes or 8 words, whatever it is that you've decided, and the 8087 will flag all the appropriate errors. If you try to do this, it continues to rotate within this stack that is defined. And as I said, the ST0 acts as the accumulator. I'm not going to go into all the details of every instruction, the 68 instructions that are provided by the 8087. This can be found in virtually any reading material that you have. But suffice to say that you as a programmer suddenly have the power of these 68 floating point instructions available to you. As long as you have an 8087 as part of your system and the 8086 operates in the maximum mode. So this is what I wanted to discuss with you around the arithmetic core processor. In the next video, and possibly the last video, we're going to be discussing something about microcontrollers, and which is really a general purpose processor built in with tons of peripherals around it. Till then, I would urge you to understand a little bit more about floating point arithmetic and how the 8087, using its instruction sets, helps you achieve those operations with minimal fuss and programming overheads. Thank you very much.